Good morning, everybody. Today we are going to be looking at an assignment that kind of combines everything we've learned in 4.5 and 4.6 together into one assignment. So you're going to be using the rational root theorem a little bit today. You're going to be using the fundamental theorem of algebra, Descartes' law of signs, and you'll be even factoring as well, solving polynomial equations. So I'm just going to do two problems with you that'll look similar to the problems on your assignment. Your assignment's only 4 problems long today because they can kind of take a little while, and it won't be due till next Tuesday. So the directions for your assignment will look like this. It'll say, state the number of complex zeros, the possible number of real and imaginary zeros, and the possible number of positive and negative zeros for each function, then find all zeros. So like I said, it's just kind of combining everything we've learned in 4.5 and 4.6. So the first example I'm going to do with you is f of x equals x to the 4th minus 6x squared plus 5. So I'm just going to start building all this stuff that it wants. First, I'm just going to state the total number of zeros that the polynomial has. If you remember, that's our fundamental theorem of algebra. The degree of my polynomial is 4, so the total number of zeros would be 4, based on my fundamental theorem of algebra. So I'm going to have 4 total zeros, whether they're imaginary, whether they're all real, whether they're a combination of real and imaginary. I'm going to have a total of 4 zeros. Now let's use our we'll use Descartes' law of signs now to determine the possible number of positive real zeros. Now if you remember from it was either yesterday or Tuesday or both, we look at the number of sign changes within our polynomial. So my first term in my polynomial is positive. So to get from this one to my next term, I had a sign change. So there's 1. From my second term to my third term, I also had a sign change. So there's 2 total sign changes in my polynomial. So that means I have a possibility of having 2 positive real zeros. And if you remember from Descartes' law of signs, it said or less than that by an even number. So less than 2 by an even number would be 0, because 0 is 2 less than 2. So the possible number of positive real zeros is 2 or 0. Now let's look at the possible number of negative real zeros. If you remember on that, we find f of negative x and look at the sign changes within that. So if I have a negative x raised to a positive power, it's just going to be x to that power. So nothing really changes for my f of negative x. So I still have 1, 2 sign changes. So the possible number of negative real zeros is 2 or 0 once again. Now I had some people asking about that or 0 part. It's just whatever number we get for the possible number of positive or negative real zeros, we just start subtracting 2 from that number until we get to 0 or to 1. Because once I get to 1, I can't go 2 because I can't have a negative number of real zeros. I can only have a positive number or 0. So here I just counted down until I got to 0, so it was 2 or 0. If I had a possible number of positive real zeros being 5, then it would be 5 or 3, which is 2 less than 5, or 1, which is 2 less than 3. So hopefully that clarifies some things. If you're still not understanding that, please make sure you're asking. So if you remember from the other day when we were talking about our Descartes law of signs, we created this table. So I'm going to be creating my table again, positive real zeros, negative real zeros, imaginary zeros, and total zeros. You guys should remember this from our notes from the other day. So I'm just going to build all my combinations of possible combinations of my types of zeros. So the first one I'm going to do is my possible number of positive real zeros was 2. That was my highest one. And I could have also had 2 negative real zeros. Now remember, I need a total of 4 zeros. So 2 plus 2 gives me 4, so that would mean there would be 0 imaginary zeros with this specific combination. Now, I could have 2 positive real zeros and 0 negative real zeros. So that would mean I would need 2 imaginary zeros. Possible number of positive real zeros is also 0. So I could have 0 positive real zeros, 2 negative real zeros, which would mean I would need 2 imaginary zeros. I have one more. I have a possibility of having 0 positive real zeros and 0 negative real zeros. So that would mean I would need 4 imaginary zeros. So the zeros that I find is going to fit one of these specific combinations. It's either going to be 2, 2, and 0, 2, 0, 2, 0, 2, 2, or 0, 0, 4. So that's the next part of what my problem is asking. I found all the possible types of zeros. Now I need to actually find the zeros. So I'm just solving this equation, this polynomial function, x to the 4th minus 6x squared plus 5. I'm solving it, so I'm setting it equal to 0. Finding the zeros of the function. So if you guys remember, I checked to see if I can factor this before I try to use the rational root theorem. And this one actually is factorable. In my parentheses, I'd get x squared and x squared. My two signs are going to be the same, and they're both going to be negative. So now I got to create my t-chart to figure out what my two numbers are. So factors of 5 are -1, -5. Those multiply to give me +5. And those add to give me -6. So there's my two numbers. So that was easily factorable. Here I have a difference of squares, so I can factor that a little further. That'd become x plus 1 times x minus 1. And then I still have x squared minus 5 equals 0. That's as far as I can factor that. So now I can start setting my factors equal to 0. So x plus 1 equals 0, x minus 1 equals 0, x squared minus 5 equals 0. Now I just start solving these individual equations for x. Subtract 1, x equals -1. Add 1 to both sides, x equals +1. Add 5 to both sides, get x squared equals 5. To get rid of my x squared with my x, I have to take the square root of both sides. So here x would equal plus or minus square root of 5. I can't take the square root of 5 and get a nice whole number, so I just leave it as the square root of 5. So I'd get x equals the square root of 5. X equals -0.5. square root of 5. And there's my 4 zeros. Now let's see which combination it fit. I've got a negative, positive, positive, and a negative. So I had 0 imaginary zeros, 2 positive real zeros, and 2 negative real zeros. And now I am finished with that problem. So we're doing all of that within one problem. I know it seems like a lot. That's why I only put 4 problems on this assignment. Let's look at the next problem that would look similar to your assignment. Oh, this one looks a little tougher, doesn't it? We have f of x equals x to the 5th minus 3x to the 4th plus 9x cubed minus 27x squared plus 14x minus 42. So first off, I'm going to state my total number of zeros. The degree of my polynomial is 5, so that's how many total zeros I'm going to have. Total of 5. Let's look at our possible number of positive real zeros. Once again, this is where we use Descartes' rule of signs. So I'm looking at all the sign changes within my function. So I go from positive to negative here. There's 1, 2, 3, 4. I have 5 sign changes. So the maximum total number of possible real zeros that could be would be 5. Now remember, it says it could be or less than that by an even number. So I'm going to just keep subtracting 2 from 5 until I get to 0 or 1. So the possible number of positive real zeros could be 5, or 3, or 1. I could have 5 positive real zeros, 3 positive real zeros, or 1 positive real zero. Now let's look for the possible number of negative real zeros. Once again, I've got to use f of negative x. So general rule of thumb, when you're plugging in a negative x, if it's raised to an odd power, then the sign is going to change in front of it from the original. So for negative x to the 5th, I'm going to get negative x to the 5th. Negative 3 times negative x to the 4th, that's raised to an even power, so that sign is just going to stay the same. So minus 3x to the 4th. Positive 9 is going to change to negative 9 x to the 3rd. Negative 27 is going to stay the same. Negative 27x squared minus 14x minus 42. So here I'm looking at all the sign changes that I have. But if you notice, all my terms are negative. So I don't have any sign changes at all. So my possible number of negative real zeros is just 0. I'm not going to have any positive or negative real zeros. That's not a possibility based on Descartes' rule of signs. So 0, negative real zeros. Now let's build our chart stating all the combinations of possibilities of the types of zeros we're going to have. So positive real zeros, negative real zeros, imaginary zeros, and total zeros. So my first possibility for positive real zeros is 5. Once again, I'm not going to have any negative real zeros. Remember, I'm going to have a total of 5 zeros. So that means for this combination, I'd have 0 imaginary zeros. The next possibility of positive real zeros is 3. Once again, I have 0 negative real zeros. So that would mean I would need 2 imaginary zeros there. My last possibility for positive real zeros is 1. So that would mean I would have 4 imaginary zeros. So my total number of zeros is going to be one of these combinations. I'm either going to have 5 positive real, 0 negative real, and 0 imaginary. 3 positive real, 0 negative real, 2 imaginary. Or 1 positive real, 0 negative real, and 4 imaginary zeros. So now we need to go and find our zeros, all of our zeros. So now time we use the rational root theorem, because I can't factor this huge polynomial. So I got to use my rational root theorem. So let's list out our factors of 42 real quick. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 7, plus or minus 14, plus or minus 21, plus or minus 42, and luckily we have a leading coefficient of 1, so that's just plus or minus 1. So I'm going to put all my factors of my constant term over my factor of my leading coefficient. Plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1, plus or minus 7 over 1, plus or minus 14 over 1, 21 over 1, and 42 over 1. So I need to go through and start testing all of these using my synthetic division. So let's test out positive 1 first. So I have 1, negative 3, 9, negative 27, 14, negative 42. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. Plus 9 gives me 7. Times 1 gives me 7. Plus negative 27 gives me negative 20. Times 1 gives me negative 20. Plus 14 gives me negative 6. Times 1 gives me negative 6. Plus negative 42 gives me negative 48. So 1 is not a factor. Darn. Thought we'd get lucky and get it on our first try. Now let's look at negative 1. So once again I have 1, negative 3, 9, negative 27, 14, negative 42. I'm going to go through this kind of quick. I feel like we're all pretty comfortable with synthetic division. Negative 1 is not a factor. Now I need to try 2. Two is not a factor. Now I gotta try negative 2. Once again, I'm going through this kind of quick because I feel like we're all pretty comfortable with synthetic division. Negative 2 is not a factor. Let's try positive 3. Looky there. 3 is a factor. Positive 3 is a factor. So I can now factor out a positive 3 by representing it with x minus 3. Then I use my coefficients from my synthetic division on this page. Use these for my new polynomial in that second set of parentheses. So I get x to the 4th. I don't have that x cubed term, so the next one's plus 9x squared. I don't have the x term either, so it's plus 14. Let's see if we can factor this before we try to use the rational root theorem again. This will be x squared, x squared. Both my signs are going to be positive. Factors of 14 are 1 and 14. Those add to give me 15. So those two are not it. 2 and 7. Those add to give me 9. So I know it's x squared plus 2, x squared plus 7. So I have factored it. Now I can't factor anything else any further. So I'm going to set all my factors equal to 0. X minus 3 equals 0. X squared plus 2 equals 0. X squared plus 7 equals 0. Add 3 to both sides. X equals 3. There's one of my zeros. Subtract 2 from both sides. X squared equals negative 2. Take the square root of both sides. I get x equals plus or minus square root of negative 2. So going back to our complex numbers, this would be x equals plus or minus I square root of 2. So x equals I square root of 2. There's one of my zeros. X equals negative I square root of 2. There's another one of my zeros. So there's 3 of my zeros so far. Let's find the last two. Subtract 7. Take the square root of both sides. X would equal plus or minus square root of negative 7. So x would equal plus or minus I square root of 7. So x would equal I square root of 7. X would equal negative I square root of 7. So as you can see, if we go back to our combinations, we had 1 positive real zero, 0 negative real zeros, and then 4 imaginary zeros. Those last 4 that I found were imaginary. They have that I value in them. I square root of 2, negative I square root of 2, I square root of 7, negative I square root of 7. My only real zero was positive 3. So these are the types of problems you're going to see on your assignment today. You guys can handle them. I feel like you can. They may take a little while. Those took us quite a bit of time, but you guys can do it. There's only 4 problems, and it's due on Tuesday. Make sure if you have any questions, please make sure you let me know and be in contact with me. And y'all have a good rest of your day. Stay warm. And good luck on all your classes today.